Yeah, I read it.
All right, here, folks. Today we're gonna talk some more about volumes and then maybe do a little optimization talk here at the end. I'm gonna start by taking a couple of questions from this set of problems. If anybody has questions from that, we can start with a couple on this sheet.
Do you have an extra of this?
Pass this back. You're welcome. Anybody got any of these bad boys they want to take a look at? If not, I'll just pick one or two, you know. Going once. Going twice. All right, well, let's pick 5. This maybe is one of the more challenging ones here. It says, let R be the region, the first quadrant, bounded by the graph of y equals e to the negative x, the x-axis, the y-axis, and the line x equals b. So y equals e to the x looks like this, right? So y equals e to the negative x is just going to be flipped across the y-axis, so it's going to look like this. And then we have bounded by the x-axis, the y-axis, and then like x equals b. So that's my base of my solid, right? Everybody's okay there? On the picture, it says that the solid, or the base of the solid, and that says the cross section's perpendicular to the x-axis. So that would be like this. Are squares, so that's my side length. And we're told the volume is 4/9, and we want to solve for the value of b. So my volume is equal to the integral from 0 to b of area of the square. So that's just going to be the y-coordinate squared dx. Everybody okay with the setup? So I'm going to simplify inside that radical. So e to the negative x squared is just e to the negative 2x. I'll do a u sub here. And then I guess let's evaluate this. So I got that. Is everybody okay? Do my antiderivative. So the antiderivative of e to the u is just e to the u. And now I'm going to go ahead and evaluate my integral, or plug my values in, do my definite integral. So now I have 4/9 is equal to negative e to the negative 2b over 2 plus 1/2. Everybody okay? Going to subtract 1/2 from both sides. To do that, I need to make a common denominator, so that would be like 18 would be the common denominator. Multiply both sides by -2. Natural log of both sides. Divide by -2. And that's an answer. If I go and I look, I guess this is equivalent, right? I can push the negative coefficient in to make it inside the logarithm to make it an exponent. So 1/9 to the -1 is 9, and there's the answer that I'm looking for. A little bit different because here we had to solve for a bound instead of calculating volume. It gave us the volume, and here we're solving for one of the bounds. But not too bad, right? If you just got the setup through. Sam?
I can't quite see that answer.
-1/2 natural log 1/9, which is the same thing as d. It's equivalent. It's not the same, but like it's equivalent. No?
So in the initial setup, the e to the -x squared, you square it because the area of a square is
S squared.
Okay.
Exactly right. Yes, 100%. Yes. Somebody else have a question here? As I did one for you guys by my choice. Do you guys have one that you tried and you were stuck on, or you weren't sure about, or you wanted to ask about, or whatever?
Do 11.
11. Sure thing. I sure hope I can. All right. So 11 says, let R be the region in the first quadrant bounded by the graphs of yada, 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 as shown in the figure above. The region R is the base of the solid. For the solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with leg in region R. So I'm just going to draw like an arbitrary leg. Oops. Oh boy, then. So there's like my leg, right? Perpendicular to the x-axis. The area for a isosceles right triangle is just going to be 1/2 leg squared. Right, because base and height are going to be the legs of our right triangle, and if they're isosceles, they're the same length. So this is just going to be, like y1 minus y2, right? It's just going to be the distance, the length of that leg. So I can tell that the bottom curve is the y equals x minus 2 squared. And the top one then has to be the x comma, or y equals 4 cosine of pi x over 4. So my leg then has to be 4 cosine pi x over 4 minus x minus 2 squared. Is everybody okay there? So my volume is going to be the integral from, for slicing up perpendicular to the x-axis, we start slicing at x equals 0 and stop slicing at x equals 2. 1/2, and then my L squared dx. Sarah, does this feel okay? Setup wise? Now, notice this problem, there's that little red calculator next to the number. What's that telling me to do? Yeah, sure as heck I'm gonna do this by hand, although I think this is, probably not doable by hand. You'd have to FOIL that thing out and you're gonna end up with like cosines and polynomials stuck together, and you're not equipped to deal with that. Maybe it's an integration by parts problem, maybe, but I can't honestly tell by looking at it whether it would work out or not. So we're going to do the integral from 0 to, was it 1? 2? Okay. Of, and then we had 4 cosine, is it 2 pi x? Who's got it?
Pi x.
Just pi x? Okay. Pi x over 4, oops, that's not where I want the parenthesis, over 4 minus x minus 2 squared dx. And then we'll just press enter. So about 3.55. There we go.
What happened to the 1 hour?
Oh, did I forget it in there? Oh, no, I did, didn't I? Thank you, Frankie. Yes. So times 1/2. Thank you. That one. Good catch. I wrote it down. Because I wasn't looking at my paper and the calculator at the same time. I lost it. Sarah, how's that? It's okay?
Yeah.
So again, hopefully after you get going on these, you realize the setup is really kind of, it tells you how to set it up on all the problems. And it's like, okay, these aren't really that bad. They're just kind of scary at first. They sound terrible. And then you realize that like, oh, this is actually the easiest setup of all of them because it's telling me exactly how to set it up in the words. So if I just know how to read it right, the setup kind of follows right away. All right. The plan for today is we're going to continue talking about volumes here just by using another technique. So up into this point, for volumes of rotation, we're rotating a solid or an area about some axis. We've talked about using disks and washers. Well, that works, but sometimes it becomes either really difficult or just impractical altogether. What's up?
I think I left my computer charger in here.
Take a look. I see one sitting in the back corner there.
Give it to Meredith.
So let's take a look at this specific area here. So this is the area bounded by the line y equals 0 and the curve y equals x squared minus, y equals 2x squared minus x cubed.
Thank you.
You're welcome. Right, so we have this guy. Right, and we're rotating about the y-axis. So you're getting like, kind of like this bowl-shaped thing, right? Everybody's okay with that? Now, you might say, okay, well, it's like a concave figure. So I'd want to use a washer to kind of describe this, right? So, like my R inner would be here, and then like an R outer would be to that part, right? Now, small problem here. What's the problem? Both being drawn to the same curve, right? Okay, well, still doable for us to get around that. What would we have to do? Let's see. I'd probably have to go and like divide this area into 2 chunks and do the volume of like this area rotated and then this area rotated. and then add those two volumes together. Ugh. Right? And how would I find this specific x value down here? Well, it's one of the maximums for this function, right? So I could take its derivative, set it equal to 0, find the critical points, do a first or second derivative test, and find that specific value. Yuck, but like, okay, could do that. But here's the problem. All of that makes it hard and inconvenient, which is a good reason to avoid doing it this way. But there's even more important reason why we would not want to try to do this as a washer problem. Is I'm going to be integrating with respect to y, right? Because I need to be incrementing up and down the y-axis, right? So I would need to rewrite this equation in terms of y. Do we have a way to solve a cubic polynomial like that? To get the x by itself? No, right? There is a general formula for a cubic, like there's a quadratic. It's nasty. But here's the thing. What if it was x to the fourth? There's a formula for x to the fourth that works in some specific cases, but not always. And then any bigger than x to the fourth, there is no like general formula, period. We've proven that. In fact, that's not just like nobody's found it yet. It doesn't exist. We've proven that you cannot do it for anything, any powers of greater than 5. So this becomes like really kind of an intractable problem altogether. That's the better reason as to why this is not just inconvenient to try to do a washer on this, it may end up being kind of impossible. Everybody's okay? So what we want to do is we want to come up with a different attack, right? We need another method for when we run into problems like this that are either A, really inconvenient like this problem is going to be, or maybe just kind of impossible because of the trying to get the x by itself nature of it. Like this problem is going to be very difficult to get the x by itself unless you want to look up the general cubic formula. And then the integral that you're going to be left with is going to be awful. So we want to come up with another method. The new method we're going to come up is called the shell method. And the idea is like kind of like peeling a potato, right? So you have a potato. And the idea is, well, maybe I can calculate the volume of this potato by just peeling it once, taking the skin, calculating the area of that skin and multiplying by the thickness, and then peeling it again, taking that skin, finding the area of the skin, multiplying it by its thickness, and adding up all those skins that I peel off the potato. Everybody feel okay about this idea? That's the idea. So instead of like slicing it into little discs or washers, here we're going to be like unwrapping it and looking at the volumes of these skins. Is everybody okay? We call those skins shells. So the natural question would be, okay, what, like if I peel a potato, the area of that peel could be like all kinds of goofy looking stuff, right? I want to think about starting to do this in a more systematic way where the peel that I'm going to get is not an irregular shaped area, but something that's going to be easy to calculate. So the idea is we're going to use a cylinder. We're going to take like a cylinder with a hole through the middle, like a pipe, and that's going to be like the shell that we're going to be peeling off. The nice part about that is it's easy to calculate, or when we unfold a cylinder, it's a rectangle, right? The lateral surface area, anyway, is a rectangle. And it's easy to calculate the area of that rectangle, because it's just going to be 2 pi r, is like the width, times the height, right? So we're going to do that where the thickness of these open cylinder shells is just going to be like a dx thick. It's going to be infinitesimally thin. We're going to add up all those volumes, and we're going to end up with the volume of the whole thing. Is everybody okay with the plan? Okay. So here's a picture of like the cylinders that we're going to be using. They kind of look like this. So when we unwrap them, we're going to end up with rectangles that are like 2 pi r h times delta r, which the delta r is like our dx, like our infinitesimal thickness. Or here's another illustration. Again, we have this open cylinder. It's just going to be the circumference of the cylinder times its height multiplied by its thickness. So, in an example, here is some function f of x, bounded from a to b, rotating it about the y-axis, we end up like this solid, kind of plunger-ish shaped thing where it has like a hole through the middle. Everybody's okay with that? We're going to build our shells now. So our shells are going to keep getting thinner and thinner and thinner, and eventually it's just going to be like the figure, right? So that's kind of it, visualizing what it is we're trying to do here. Does everybody feel okay? So in general, well, not in general, but this figure up here that we looked at, the volume is just going to be the integral from a to b, 2 pi x f of x dx. Again, 2 pi r times h times like delta x, or delta r. So let's return to our original problem. Again, where this is like r, h, and like delta r. Let's go back to that original problem we had at the start and use this new method to calculate our volume. Is okay? All right. So, here's that same graph. I've drawn in one of these cylindrical shells to help us visualize what it is we're doing. So the distance from the axis of rotation to some point on the function, that's like my radius, right? If this is the function, or if this is the point x comma 2x squared minus x cubed, r is just the x cubed, right? And then the height of my cylinder is just going to be the y-coordinate. Is everybody okay visualizing what we're seeing here? So my volume is going to be the integral with respect to x of 2 pi r times h delta r. Does everybody feel okay there? And my bounds of integration are dependent on my radius, right? So the smallest radius would be like here, where the radius is 0. And the biggest radiuses would be for like the end one, where the radius is 2. So we're kind of going from 0 to 2. Everybody okay with that idea? And look at how nice and neat that is, right? Is there going to be any problem computing this integral? No, man, we just pull the 2 pi out and distribute the extra, and it's about as easy as they get, right? Was it difficult to construct this integral? Did I have to break the area into two pieces and do two volumes separately and add them together. I have to solve this impossible equation to get the x by itself or anything. Just like all just kind of fell right into place really nicely. Anthony?
So whatever you're using with respect to is just going to be x or 2x, either in radius or height.
So what I would, here's the way it's going to work. So when we did shells and washers, if we rotated about the axis of rotation, right? We would draw a radius perpendicular, and that was kind of telling us what we're incrementing by, right? Whether it's dx or dy. Everybody's okay there? Here it's going to be like the opposite. So if we are drawing our radius perpendicular to y, it's going to be a dx problem. If it's perpendicular to x, it'd be a dy problem. But you can do this both ways.
And if it were a dy problem, the radius would be a polynomial and the height would be a...
If it was a dy problem, you would not use the shell method to do this, because you'd be running into the same problem you had with trying to use it as a disk. If we rotated about the x-axis, this is just a convex figure. I'm disking that all day long, right? Like it's the easiest disk problem you could probably get. You know what I'm saying? So the point of the shell method is that it allows us another tool to avoid having to do horrible mathematics, right? So the end goal here is you have three methods, disk, washer, shell. Can I pick the one that's most convenient to avoid having horrible mathematics to do? Like to solve some polynomial for x where I have no business being able to solve this for x. Or break up this volume into different, having to do two separate volume problems instead of just one. We want to avoid having to do that. So the shell allows us to do this. Notice if I was doing this, rotating about the x-axis here, I would avoid the shell, and I'm just doing a disk, because I'd have the same problem before where I have to get everything in terms of y, and I can't. It's a cubic. I can't solve that for y. Or get the x by itself, so it's in terms of y or whatever. You know what I mean? So does that answer what you're trying to get at? Let's do some more examples. Okay? This is the concept for today. We're just going to iterate on this and do examples, doing some setups. All right. The next example says, use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals square root x from 0 to 1. So here we're rotating about the x-axis. I want to point out, I would not do this as a shell problem. It's fine to do it as a shell problem. It's not hard as a shell problem. If I have a convex figure, though, I'm doing disks almost without thought. So if you're thinking, why would I do this as a disk problem? My answer to you is I would. But it's not a difficult shell problem. Let's do it as a shell problem also, just to get you, show you what happens when we rotate about a horizontal rather than a vertical. So when I draw the radius for my cylinder, I'm going to start on my axis of rotation and draw to the curve. That's my R, right? This is the point xy. R is the y coordinate. Everybody agree? So what I need then is, this is the form x comma square root x. That doesn't help me. I need this in the form y comma y squared. Right. So my radius should be y squared. Is everybody okay with that? The height of my cylinder is going to be drawn through the solid part of my figure back to the boundary. That's my height. Is everybody okay with that? So this distance is 1. This distance is x. So h should be 1 minus x, right? Everybody agree? And since I know x is equal to y squared, oh my goodness, guys, y squared comma y. Yeah. Okay. Should be 1 minus y squared. Everybody okay? Yes or no? Do you want to start over and do it again? Did you not follow? No one's saying anything and you're just all kind of staring blankly like, he's doing stuff and I feel like I should understand it, but I don't. Some feedback would be good. Do you want me to just start over on this? One more time? Okay. Just say so. It's okay. You don't have to be embarrassed. Be like, I don't know, Mr. Kulik. Can you say it all over again? All right. Let's start. We're rotating about a horizontal axis. Tells me it's a dy problem. I'm always going to be drawing my radius. From the axis of rotation to the curve. That distance is going to be, since the x values are the same, it's going to be the difference in the y coordinates, right? This y-coordinate on the x-axis is 0. So r is just this y-coordinate here. But do you agree? Is that fine? The height of my cylinder is always going to be drawn back through the shaded region to its boundary. In this case, that's the line x equals 1. This distance is 1. This distance is x. So that height is 1 minus x. Does everybody see that? Now, because I'm integrating with respect to y, I can't have an x here. So I need to rewrite x in terms of y. You know y is equal to the square root of x. So y squared is equal to x. Okay? So we have 2 pi times r times h. Does that feel okay? Yes?
Could you repeat where you got the 2 pi?
It's part of the formula. Remember, we're taking a cylinder with a hole through it, and we're calculating the volume of that. So to calculate its volume, we're unwrapping it so it makes a rectangular prism. the base of it is the circumference of the cylinder, 2 pi r, times the height of the cylinder, h, times its thickness, dy. Is that a good question? If you're not sure what's happening, like, you ask the question, I'm happy to re-explain. What do we still need here? Bounds of integration, right? We're integrating from something to something. We're going to be integrating from y values, right? Our radius is a y. Our shortest radius can be 0. Our longest radius would be 1. So we're integrating from 0 to 1. And again, we're left with a problem that's pretty easy to integrate by hand if we wanted to. Again, you pull the 2 pi out front, distribute the y through, and it's a pretty darn easy polynomial integral. What do you guys think? Now, for the record, as a disk, that's all I'm doing. That's what I would have done. This is a test question. It's like, find the volume. I'm doing it as a disk, right? That's pretty stinking easy in comparison. Do you see it? Pi r squared, where the radius is just going to be the height of the, the y coordinate, square root x. Woo! Integral of pi x. You can handle that. Like, sounds good. What is that going to be? It's going to be pi over 2. All right. Let's look at another. It says, find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. Here's x equals 2. Everybody okay with the picture we're looking at? This is a canonical example of a problem that you would want to do using a shell as opposed to a disk or a washer. The reason is, if I try to draw my inner and outer radius from the axis of rotation, they're both on the same curve, right? When my curve is not 1-to-1 in the direction that I'd be slicing, boy, I want to do a shell. If we're rotating about a horizontal axis, no problem, I'll disk or washer that all day long. But if it's a vertical, this is now a classic shell example. Is everybody okay? You see what I mean by 1-to-1 in the direction that we're slicing? And if we're slicing this way, I'm hitting this function twice. That's a shell situation. Everybody okay? All right. So let's start drawing our shell stuff. So my radius is always drawn from the axis of rotation to the curve. So I know this distance is 2. This distance is an x. So my radius should be 2 minus x, right? I guess before we do this, we could acknowledge, since we're going about a vertical, this is going to be a dx. Whoa, boy, what just happened? This is going to be a dx problem. I guess I could do that to start with. Everybody okay so far? Now my radius is 2 minus x. Where's the height going to be for my cylinder? It's going to be drawn through the shaded region to the boundary. So that's my h. Are you okay with that? Is that a y distance or an x distance? So y distance, because it's straight up and down. In fact, if this is the point x comma y here, that h is just the y coordinate, right? And because the y coordinate is just x minus x squared, that's my height. Is everybody okay there? Now my last thing I need to do are the bounds. So my shortest radius would be 1. My longest radius would be 2. Everybody see that? Everybody agree? The radius is 2 minus x. If I subtract 2 from both sides, get this. Divide by -1, the inequalities flip. Since we're integrating with respect to x, I need that bound in terms of x. Notice that this matches up really nicely. Come on. With where the function intersects the x-axis, which is the typical case. How is this going, guys? I have some more examples. Should we keep going? More exampling? So this is part of the homework. If I look at number 3, this is our picture here. So this is the graph of cube root of x. And we have y equals 0, x equals 1, and our curve. So this is our shaded region. Try to set this up using a shell method. Oh, it says we're rotating about the y-axis. That's part of the direction. You need that. So try setting this up. Just make a sketch somewhere on a scrap piece of paper or whatever. We'll give you guys a couple minutes to set it up. Don't bother finding the actual answer. Just do the setup for right now. That's the part that's hard for us because it's new. And then I'll write in the answer if you guys don't see what I did. Let me ask some questions. We'll do this a couple of times and then talk about some opt stuff. DX problem, right? Radius drawn from the axis of rotation, back to the curve. Well, that's just x. The height of the cylinder, just drawn back through the shaded region. So that's the y coordinate, or in this case, just cube root of x. I'm done. Setup complete. Keep in mind that if you would have done this using our old method, this would have been a washer method, right? I think the integral is a little bit more complicated that way. Right, pi r 1 squared minus pi r x squared, is that right? I don't know, whatever. So far so good? Let's do another. Oh, we didn't put the bounds on. What are the bounds? Yeah, 0 to 1. Sorry. So this one is, let me just check. That's this one. So this is still doing this. This is y equals e to the negative x squared. And then we're going here. Right, I think that's right. Yeah. So again, try setting this one up. Give you a minute to work on the setup, and then we'll go over and write in the answers. You guys can ask about it if you're not sure on what I put up there. If you're not sure about anything, please interrupt. Ask some questions, if you're like, okay. We're just starting our setup. You guys all have the formula down, right? 2 pi rh delta x or dx or whatever. dy, depending on the direction that you're rotating. Oops. That was okay with the R and the H location? So R is just X and H is just Y. Bounds of integration should go from 0 to 1. That okay? Keep on going. I got some more, or at least one more. Here's this one. So this is xy equals 1, and then between y equals 3, y equals 1, and then the curve. Let's just do that. It's a little neater. Ah, x-axis this time. Thank you. So that tells us immediately that this is a dy problem. Everybody drawing the same R and H that I did? Yeah, Ava?
I'm sorry if you already said this.
No, let's
but
go ahead.
How do you know where to draw the R and the H? Like, is there a specific?
So I'm drawing an arbitrary R and H,
Okay.
right? My R always goes from the axis of rotation, so in this case it's the x-axis, to the curve.
Okay.
So I picked somewhere on the axis of rotation, drew up to the curve. Now obviously I can't pick out here because the curve doesn't extend over that.
But you can pick like any.
I could have picked here, it
Okay.
doesn't really matter. And then the H is always drawn back through the shaded region to the boundary. So the H should always be under the shaded region.
Okay.
Is that
Yeah.
okay? So R is just the y coordinate for that point, right? If this is the point x comma y, R is the y coordinate, H is the x coordinate, but the problem is I need to be it in terms of y, this is in terms of x, but I know that x is equal 1 over y. And then I just need some bounds of integration. They should be from 1 to 3. Yeah, that's correct. Again, R is the radius, right? The shortest radius would be here, where R is equal to 1. The biggest radius would be somewhere in this area here, where R is 3. And then that's just about the easiest integral left alive. Integral of 2 pi from 3 to 1. So it's 5 pi is your answer. Ooh. So for tonight's homework, we ask you to work on, these problems from 3 to, 25, some of these odd ones in here. While you're doing these, worry about the setup. If you feel good on your integration, I would just type the answer into my calculator, or the problem into my calculator, and have the answer spit out and check it in the back of the book to make sure your setups are good. If you feel shaky still on your integration, do a couple by hand to practice, or if you're like, I could still use some sharpening on this. There's many of us in here that probably still feel a little shaky on doing these integration by hand skills. This is a wonderful opportunity to practice that, since they're all definite integrals. You can do it by hand and check the answer in the back of the book and use your calculator and make sure, you can do the calculator with your setup to make sure your setup is correct. And then you can grind it by hand and make sure you get the same thing, right? It's a nice situation where you know that you can check your own work. On the virtual day, your assignment is going to be 37 through 45 all. Those problems, you could do disc, washer, or shell. Your job would be to pick the most appropriate method, okay? So there's some where, like disc or shell may not make any kind of difference. Like they're both pretty easy, or like, you know, there might be a washer or shell where it's like there's not much difference, they're both pretty easy. But there will definitely be somewhere like the washer is way easier than the shell, or the shell is way, or the disc is way easier than the shell, or the shell is way easier than the washer. In fact, like the washer is kind of impossible. So the hardest part for most students is being able to choose the appropriate method for the problem, that you've done enough of these things and spent enough time with this that you can spot from the two-dimensional picture which method is going to be the better one to choose. Or at least know once you get into it, be like, this is not going my way, I'm doing the wrong thing here. And the only way to do that is to, you know, to try problems, to do problems, to get a feel for the pattern. What kind of two-dimensional picture should dictate the setup? What am I looking for in the two-dimensional picture? We've talked about the things that really indicate a shell versus a disc or a washer. You know, if it's convex, almost always I'm going to do that as a disc problem. I'm not going to bother with the shell. Shell might be equally easy, but like the discs are usually never hard. The only case where I might shy away from the disc versus the shell is if if the solve for X piece is really inconvenient. The shell, because it's going in you're using the opposite variable for integration, would allow you to skip over that. Might do it in that sense, but that's kind of the gist of it. Good news for you guys, come AP exam time. The AP exam you will be taking, the AB exam, the shells are not part of the AP exam. Now in your college calculus class, when you do this, the professor will surely expect you to be able to do all three of them. I will expect you to do all three of them. The AP exam you'll be taking, there are no problems that it will be more advantageous to do it via shell than it would be by disc or washer. Just to give you the heads up. Okay, so we would not need to have that method. You can still use it. They will mark it correct if you use it. But there will be no problems on the AP exam you will be taking that will be more beneficial to do as a shell rather than a disc or a washer. This will not be the last topic we do in this course where it's like, we're doing this, but it's not on your AP exam. I will continue to point this out to you, that like we're doing something now that like your college calculus course would expect you to be able to do, but is not part of your AP exam. So we'll see this a couple more times. There's, I don't know, 3 or 4 other stray topics that I will do where that's the case. Okay? Should we do a little bit of op stuff? Probably. Ideally, I'd like to be doing the opt test at some time next week. I would do similar format that we did for the related rates. So we'll have like a little 45-minute window. You guys get like 5 multiple choice questions, 3 free response. You get to choose 2 to complete. 30 points total, same kind of format as before. Everybody okay? Which opt sheet did you guys want to look at? Probably have time for 3. Okay, we can look at opt 3. Okay, what do we, which one on opt 3 is the biggest headache? It's 4, right? The rectangle inscribed in the circle. That was the hardest one on this sheet, in my opinion. So it says, let's read it first. A rectangle is inscribed in a circle of radius r. Write the area of the rectangle and then find the maximum possible area in terms of r. So to model this question, I could not remember all the geometry theorems that I would have needed to do this. So I'm going to embed this into an XY axis. I think will make this the easiest for me. So I just kind of did that. And then we'll have like and do a very good job of lining this stuff up. I'll just make a really big point there. It will look good enough. So there's my like rectangle embedded inside of that circle. So far so good? So like this is the point x, y. This would be the point x negative y. This would be the point negative x negative y. This would be the point negative x positive y. So far so good? Now the area for a rectangle is just like length times width, right? So let's say that side's length, that's width, and this side is length. Yeah? So width is just going to be the distance from the point negative x positive y to positive x positive y. Well, that's just going to be 2x, right? Length is going to be the distance from positive x positive y to positive x negative y. That's just going to be like 2y then. Everybody feel good? What's my issue? Is that my area is still in terms of two different variables. Bummer. So what I'm going to do is I know that this distance is a radius of the circle. That's constant, that's r. This is y, this is x. So I make a right triangle here. So this would allow me to rewrite x or y in terms of the other variable and this constant r. Does it matter which one I choose to get by itself, x or y? Not a bit. I'm going to use x's. Yes, sir.
Wouldn't length and width be the same size?
Well, I drew it as a square. It doesn't necessarily have to be a square, though.
How could it be in a circle?
Right? That's still a rectangle inscribed in the circle. Is that okay? Okay. So there's that. Now, what can I say about y? Since y is going to be the length, I can discard the negative. So my area function then in terms of x would be 2x times 2 square root r squared minus x squared. And then I should cook up a domain for x. What's the smallest possible value that x could have? Yeah, right, can't be 0 or smaller. Because if it was, like my rectangle would just be a straight line like this, and that ain't a rectangle. Okay, what's the biggest possible value for x? Capital R, if it was, then my rectangle is just this horizontal line. That ain't a rectangle. Also, you could look at if it was less than 0, this piece becomes negative, so I'd have a negative area. If x squared was bigger than r, the part under the radical would be negative. Can't do that. Does that feel okay? All right. So here's my area function. That's my answer for part A. To get part B now, I'm going to have to do a optimization, a first or second derivative test on that function there. When I look at that, I see a product rule and a chain rule. Yuck. I'm going to do a little bit of algebra to avoid the product rule here. So what I'm going to do is I'm going to rewrite x as the square root of x squared. I'll make that a 4. Everybody's okay that I just rewrote x as the square root of x squared? The advantage there is it allows me to distribute that x squared inside of my radical. Which eliminates the need for a product rule in my derivative. It's fine if you did it and didn't catch that or didn't do that simplification and you do the product rule. It makes the algebra later a little bit more complicated because then you have to like add fractions together and it's kind of a pain in the neck. If you do it this way though, you can avoid that, which is mucho beneficial. So I'll do my derivative. So I'm going to have 4 times the derivative of the outside, which is 1/2 inside to the negative 1/2, times the derivative of the insides. Everybody okay there? And so let's see. I see a factor of 2 in here, right? So I can do that. And if I clean this up, I could write this as 4 times r squared minus 2x cubed over the square root of r squared x squared minus x to the 4th. I'm now going to find the critical values. So I'm going to take that derivative and set it equal to 0 and doesn't exist. So I can see that if x equals 0, I end up with a 0 denominator, but that's fine because x equals 0 was not part of my domain anyway. And the same thing if I have x is equal to r, I'd have r to the 4th minus r to the 4th. That's 0. But r isn't part of my domain anyway, so that's fine. So it turns out that there is, no values for x that make this derivative undefined that are still in the domain for x. So that's good. Okay. So now I'm just going to set this thing equal to 0. This is a fraction. When is a fraction equal to 0? When the numerator is 0. Yeah. So I can just forget about the denominator. Woo! I forgot the x here. R squared x. Sorry about that. Everybody good? How do I solve this for x? Great. Factor what?
Factor B.
Good. Yeah, let's divide the 4 off while we're at it. Sound good? I can discard x equals 0 as a solution. Why? It's not in the domain, right? X had to be greater than 0. So I just have this guy. We'll subtract the r squared over, divide by 2, and then square root both sides. And I can discard the negative answer because x has to be greater than 0. So this is my value. Now I could check that this is, I would want to check to make sure this is a maximum and not a minimum, and this isn't some weird unbounded situation. Pretty sure it's not. But if I pick a value that's less than this, like r over 2, I would have like r over 4, or r to the 4th over 4 minus r to the 4th over 32. And then the top will be positive also, so it's like positive. If I pick something bigger than this, like r over 4, r over, let's think here, like r over, it stinks. It's going to be negative. So this is a maximum. So then I just need to compute A of this guy, which was, going back to get my function for A, 4 times the square root of r over square root 2 squared times the square root of, oh, I shouldn't do that. I want this. So I have 2 r over square root 2 times square root r squared minus r over root 2 squared. Everybody's okay? So this and this reduce, and that gives me just root 2r. R over root 2 squared becomes r squared over 2. R squared minus r squared over 2 becomes r squared over 2. Which is r squared. Is that what I'm supposed to get? Don't tell me I moved something up here. Oh, I'm so dumb. I forgot that too. So there's supposed to be a 2 here. So that'll be a 2 there, 2 there, 2 there, 2 there. Sorry about that. Yay! It is 2r squared. Yes, it's a square. And then you were right. That is the shape that maximizes. Hopefully that's not a surprise. But asking for the area in terms of r maybe wouldn't have been like super obvious with it, like, is this a square? Ooh, all right, maybe. Anyway, that was the worst one on this set 3. I thought anyways. The algebra is the yuckiest. That's for sure. And the setup was a little bit of a challenge if you didn't try to embed it to the XY axis. That made life much easier. Because I had trouble trying to come up with like X and Y in terms of R, or the length and width in terms of R, and getting one variable in there. That was going to be a problem for me. Anyway. Are there, still have, I don't know, I guess we don't have much time left. What do you guys think? We'll talk on Monday about setting a date for the opt test. I'd like to do it next week. So kind of think on that. We can do it on, sounds like there's a big biology test on Friday, is that accurate? one bio people, some bio peoples.
The person's Wednesday.
So I don't know, is this HL or AP?
I think both of them.
You think both of them?
Both have next week tests.
HL is.
The test is Wednesday.
Oh, the HL test is Wednesday?
Oh,
That's miserable for me.
HL is Wednesday and then AP is Friday.
You know what? Is this all Elwood?
Yeah.
Can you get on the same day, Elwood? Come on
I
now.
wouldn't mind for me.
You're killing it.
Yeah.
Maybe so that's great.
I'm going to her.
You talk to her and we'll talk on one day next week about setting it up.
Wait, let's have we push ours to Friday.
She could move next week.
She could, we'll ask her if they
You asked her.
That would be
No,
nice.
but like, I'd rather.
Be like, all
I'd
of the
rather
AP
take it
Calc
on
students
Tuesday
are
than you guys take it.
in one of these two classes. Can we just have this on the same day so I can have our AP Calc test on a different day
I'm
than
going
the
to
bio
her,
test?
Right after this.
Like, you can do new stuff on
Yeah,
Wednesday if you need
I
to,
would
and we won't get behind.
Right. I don't even, you've already done the lessons? You have anyone else, do you?
Yeah,
I think
we're
we
done.
do.
No, we're done. We have the POGL over the async day, and then we have a study guide on Monday, and then
She's
the
never
test.
given us a study guide.
Well, now she's giving us one. Like,
Probably because it's gonna be.
it's like a book
Because we're actually learning new stuff for
Does she not
like.
give you guys the AI study guide?
She never gives us study guides, ever.
We get these like crappy AI ones that are nothing like.
What do we teach someone? It's only like 15 pages long.
No, cause like, she would give us study guides, but the day before the day before the test, so the night before the test, she'll give us the study guide, but none of it's filled out, it's all questions. I was like, okay. Wait, but
I
now
just don't
it's.
even give you a study guide, I just tell you
No,
like
no,
what
no,
are
like
what
the
the
study
test gonna
guide
be on.
pages.
Yeah, that's
Try to be really
like,
specific.
I feel
I
like
like
the
the
study guide is slideshow.
No.
What's that?
I like the multiple choice questions.
Yeah, I give you like then I give you like a mountain of AP style questions that usually like I'm pulling from these. So good luck finding the ones that you need to worry about, but I just do all of them. Yeah, but that's what I want.
I know,
That's-
she's
that's
just gonna
good
give us
practice.
the questions.
I thought she
This
wrote
one's
us.
for the exact same effort.
I was
I know.
Oh, no, silly
I have used some of these, well, you exact, or just changed it moderately, like I think for the last one, like it was the same graph, but the integral was, like I changed the factor out front, instead of like 2, it was like X or
It's
something.
usually like pretty much the exact same every week, the numbers change.
I really love it.
That's
Like,
it, like,
right now.
I have to. I think that until like that's
We're going blind sometimes with You go
Like, you guys, like, we only have like half of a problem.
Was it? Yeah, I know, exactly, you're right.
No, I'm not even gonna. I have to, 4 people.